Welcome back. Still on the BSM model, we shall learn the option Greeks. In this order, we shall learn the delta, gamma, theta, vega, and rho. Let's jump right in. We've learned that there are 5 key inputs to the BSM model: the underlying asset price, exercise price, time to expiration, asset price volatility, and the risk-free rate. In this lesson, we shall learn 5 measures to characterize the sensitivity of the option value to these factors. The delta and gamma measure sensitivity for the underlying asset price, theta for time to expiration, vega for price volatility, and rho for the risk-free rate. Collectively, these 5 measures are known as the option Greeks, which are the measures of sensitivity of the option value to changes in the various inputs. Let's go through each of them. For this lesson, we shall focus on the value of European stock options, in which the underlying stock is assumed to pay a continuously compounded dividend yield, denoted by lambda. Option delta is the change in option price for a given small change in the price of the stock, holding everything else constant. We can quite easily infer option delta from the BSM model. The delta is simply the coefficient of the spot price term. For a call option, the delta is ND1 discounted by the dividend yield. For a put option, the delta is minus N minus D1 discounted by the dividend yield. To help us visualize, let's plot the relationship between option value and the underlying stock price. At the expiration of a call option, the option expires out of the money if the stock price is lower than the strike. The value of the call option must be 0. If the option expires in the money, the increase in the value of the call option exactly matches the increase in stock price over the strike. The line here should have a slope of 1. In essence, at expiration, the delta at prices lower than the strike is 0, and 1 at prices higher than the strike. However, before expiration, the value of a call option has speculative value, so the relationship between call value and stock value should look something like this. The speculative value is the premium here, which we will discuss more later. The delta is the slope of the tangent to curve. So, for example, if the current stock price is $50 and the exercise price is $45, ND1 is 0.785, there are 2 years to expiration, and dividend rate is 3%, the delta at this point is 0.74. This means that if the price increases by $1 from this point, the call value should increase by 74 cents. So, as you can see, the delta will vary according to the stock price. If the stock price is close to 0, delta will also be very close to 0. If the stock price is very high, it should converge to 1 if there is 0 dividend yield. However, if the stock pays dividends, which is a benefit to the short, the call price should be correspondingly lower to compensate the long. As the stock price increases, ND1 converges to 1, so based on the equation, delta should converge to this dividend discount factor as the stock price increases. In essence, the delta of a call option increases from 0 to the dividend discount factor as the stock price increases. Now let us apply all the same arguments for the delta of the put option. You may want to challenge yourself and draw out the relationship between the put value and stock price. Let's first determine the payoff at expiration. The put option expires out of the money if the spot price is higher than the strike, so delta at expiration here is 0. Every dollar that the stock price ends up below the strike is added to the payoff. So the payoff should look like this, with a cap at the strike price, since stock price cannot be negative. The slope of this line is -1, so delta is -1. Before expiration, there is likewise speculative value, so the curve should look something like this. At each point, the delta is calculated as minus dividend discount factor times N minus D1. So now you see why there is a minus sign, as the tangents to the curve all have negative slopes. When deeply out of the money, the delta is close to 0, but still negative. When deeply in the money, the delta converges to minus dividend discount factor. So in essence, as the stock price increases, delta increases from this value to 0. This is an increase as we're talking about negative values here. So one key takeaway for option delta is that it always increases with stock price. One major limitation of option delta is that it is valid only for small changes in stock price. This is because delta is linear, whereas the actual relationship is a curve. If there is a jump in stock price, the estimate of the change in option value using delta alone is less accurate as it misses out on the increase due to the curvature. For larger changes in the stock price, we need better accuracy. And that brings us to the second Greek, which is gamma. Gamma measures the rate of change in delta as the underlying stock price changes. In other words, gamma captures the curvature of the option value versus stock price relationship. Since delta always increases with stock price, gamma is always positive for the long position of both call and put options. If you observe the curves, the curvature is deepest closest to the exercise price of the options. Gamma is highest for at-the-money options. Deep in the money or deep out of money options have low gamma. That is, the delta hardly changes with the stock price. Gamma is useful to estimate the change in option value due to a large jump in stock price. We just need to add on this convexity term, which estimates this portion of the change in option value. You may find this somewhat familiar, as it is similar to how convexity improves the estimate of change in a bond's price in response to a change in interest rate. So, for our example, let's say gamma is 0.035, we can estimate the increase in call value to be $9.15. If we had only used delta, the estimated increase of $7.40 would be rather inaccurate. This same formula can be used for calculating the value of a put option as well. Let's look at an example. Given the following data, estimate the change in value of a put option if the underlying stock price increases to $100. Pause the video now and work out your answer. And we're back. Let's first calculate the delta for a put option, which, if you recall, is a little different from that of a call option. Plug in the figures, we get minus 0.4467. As expected, delta for a put option is always negative as the curve is downward sloping. We're told the stock price increased to $100, an increase of $20. As this is quite a large change in price, we should make the curvature adjustment as well, which is to include the gamma adjustment. Figures in, we get minus $1.93. The put option value should decrease by just $1.93 if the stock price increases from $80 to $100. Earlier, we alluded to this notion of speculative value, which accounts for the higher value of the option any time before its expiry. This speculative value is a function of the time to expiration, stock price volatility, and the risk-free rate. Let's examine each of them, beginning with time to expiration. For both call and put options, the speculative value decreases with the time to expiration. As an option approaches its expiry date, the curve converges to the payoff curve at expiration. It's not hard to see why. The shorter the time to expire for a European option, the lower the chance for the stock price deviating significantly from its current price. Thus, its speculative value declines until it is zero at expiration. Theta is the change in option value for a small change in time. For example, if we plot option value against time, and this is the expiration date, the call option that is at the money may have its value at initiation plotted here, and the value at expiration is zero. Theta is the slope of the tangent on this curve. Since the curve is downward sloping, theta must be negative at any time. Theta is close to the negative side of zero at initiation and decreases progressively as the option approaches expiration. This means that speculative value of the option decays faster when the option is about to expire. For put options, as the curve also converges towards the payoff curve at expiration, its speculative value also decreases over time, so theta is negative at all times. Likewise, the speculative value decays faster when the option is about to expire. Next, stock price volatility is also another important factor that affects speculative value. In general, speculative value increases with stock price volatility. Stocks that are more volatile have a higher chance of deviating significantly from the current price, so the speculative value for its option is higher. Likewise, we can plot the relationship between option value and stock volatility. For a call option, value increases with stock volatility, so the curve is upward sloping. Vega measures the sensitivity of the option value to the volatility, so it is again the slope of the tangent to the curve. Vega tends to be lower at lower volatility and increase with volatility. It's interesting to note that zero volatility corresponds to a risk-free asset. The call option value at this point corresponds to the risk-free return. The corresponding put option should have zero value if volatility is zero. And finally, our last factor, the risk-free rate. It's easier to observe the effect of risk-free rate from the BSM model. When the risk-free rate increases, the discount factor decreases, so this second term decreases for the call option, and this first term also decreases for the put option. The value of the call should therefore increase with risk-free rate and value of put decrease with risk-free rate. Likewise, we can plot option value against the risk-free rate, all else equal. Value of call should increase with risk-free rate, and value of put should decrease. Like the other Greeks, rho measures the sensitivity of the option value to changes in risk-free rate, so once again it is the slope of the tangent to the curve. Rho should be positive for call options and negative for put options. In most cases, you may observe the curves to be quite flat. That is, rho is a very small value compared to theta and vega. Rho is therefore not a very important sensitivity measure for option valuation. To summarize, delta is the sensitivity factor of the option value to the underlying asset's price movement. Value of a call increases with the underlying price, so delta is positive. Value of a put decreases with the underlying price, so delta is negative. Theta is the sensitivity towards time to expiration. Both call and put value decrease as time progresses towards expiration, so theta is negative for both. Vega is the sensitivity towards stock price volatility. Both call and put value increase as volatility increases, so vega is positive for both. And rho is the sensitivity towards risk-free rate. Call value increases with risk-free rate, so rho is positive. Put value decreases with risk-free rate, so rho is negative. Risk-free rate is the least significant factor for the BSM model, so the magnitude of rho is rather small. And that concludes this lesson on option Greeks. See you at the next lesson, where we conclude with a discussion on delta hedging and implied volatility.